Hello everyone, this is Ümit Alkuş. Today we will discuss the chapter 2, that is motion along a straight line. First, let me outline the topics we will discuss today. Position and displacement, average velocity and speed, instantaneous velocity and speed, acceleration, one-dimensional motion with constant acceleration, and free fall acceleration. The branch of physics describing the motion of bodies without considering the causes of the motion is called kinematics. In this chapter, we study only one-dimensional motion. That is, we consider the motion of bodies along a straight line. This line might be horizontal, vertical, or even slanted, but it will always be straight in this chapter. Later on, we will discuss 2- and 3-dimensional motions, which all depend on a solid understanding of the basic concepts of one-dimensional motion. They are displacement, velocity, and acceleration. Objects in this chapter will be considered as particles. A particle might be point-like, such as a small bead, or it might be a rigid body, like a car, whose every point moves in the same direction at the same rate. That is, it moves like a particle. Consider an object which undergoes a one-dimensional motion along the x-axis shown in this figure. The position of the object is given by its x-coordinate with respect to the origin. Then, if the object is said to be located at x equals 2 meter, we understand it is 2 meter in the positive direction from the origin. If it is at x equal minus 3 meter, this time it is 3 meter in the negative direction from the origin. The change in the position of the object is called displacement delta x, which is given by this formula. And it is in meters, because it is the difference between the positions. Here, x1 is the position of the objects at time t1, and x2 at a later time t2. The displacement of an object may be negative, positive, or zero. In other words, displacement is actually a vector quantity, which has both magnitude and direction. For one-dimensional motion, we do not, however, need to use the vector properties of displacement. Plus and minus signs will be sufficient. We will usually show the time-dependent position x of t of an object as a position versus time graph, as shown in this figure. The average velocity gives us a raw estimate of how fast an object undergoes a displacement over a definite time interval, which is defined as delta x over delta t, that is x2 minus x1 over t2 minus t1, and it is in meter per second. As you can see in this figure, average velocity is the slope of the line passing through the points t1, x1, and t2, x2. As a result, we can extend the preceding equation as the tangent theta of this line. Closer look shows that the ratio of the corresponding perpendicular edges of this right triangle gives the tangent theta, that is, the average velocity. Another important quantity is the average speed, and it is defined as the ratio of the total distance covered by an object to the time interval delta t. You see, it is also in meter per second. Note that since the total distance is always a positive quantity, so is the average speed. In other words, C average does not have direction, so that it is not a vector quantity. Instantaneous velocity, v of t, of an object gives us the information about how fast it is at any given instant t. It is the limiting value of the average velocity as delta t goes to 0 at that instant. You see, it is also in meter per second. Therefore, v of t is the time derivative of position x of t, that is, v of t is the rate at which the position x of t changes with time at any given instant. The magnitude or absolute value of the velocity is called speed. If the velocity of an object changes with time, we say that the object accelerates, and the rate at which its velocity changes is called its acceleration. Let the object have velocity v1 at time t1 and velocity v2 at a later time t2. Then its average acceleration is defined by this formula, delta v over delta t. Here, delta v is v2 minus v1, and delta t is the t2 minus t1. As we did in defining instantaneous velocity, we define the instantaneous acceleration of an object at any given time as the limit as delta t goes to 0 of the average acceleration. Then the result is the dv over dt. So it is the time derivative of velocity, and it is in meter per second square. Acceleration is the second derivative of displacement. A of t is dv over dt, and v is the dx over dt. So the result is the second derivative of the position with respect to t. Since acceleration is such a quantity that has both magnitude and direction, acceleration is also yet another vector quantity, just like displacement and velocity. In this figure, we show successively the curves of the acceleration, velocity, and displacement of an object as an example. You should note how the velocity curve is obtained from the displacement curve and the acceleration curve from the velocity curve, or vice versa. The velocity curve can be obtained from the acceleration curve, and the displacement curve can be obtained from the velocity curve. Sometimes, in some texts, the word deceleration is used when an object is slowing down, that is, when its acceleration is negative. It is important to notice that a negative acceleration does not necessarily convey the meaning slowing down. Whenever acceleration and velocity have the same sign, say plus plus or minus minus, the object under question speeds up for all time. Whenever they have opposite signs, the object first slows down, then stops momentarily, and speeds up towards the opposite direction. In many daily life problems, the object under question moves with constant acceleration, or its acceleration can be assumed to be approximately constant. This figure shows successively the curves of acceleration, velocity, and position for an object moving with positive constant acceleration. In the following, we will derive some formula that can be employed in solving one-dimensional problems involving constant acceleration. As we discussed earlier, an expression for position can be obtained from velocity, since velocity is the first time derivative of position. However, we do not know v yet. As in the case of position, we use the fact that acceleration is the first time derivative of velocity. Then we multiply both sides of this equation by dt to get rid of differential equation. Now we integrate both sides in the interval 0 to t and v0 vt respectively. In the right hand side, take a out of the integral sign, since it is a constant. Therefore, integration applies only on time by the same way as in this case. Here we use the fundamental law of calculus, that is, integral of differential of any function is nothing but the function itself with appropriate endpoints, and we obtain this result. Finally, by taking this to the right hand side, by changing its sign, we get v equals v naught plus a times t. Now it is time to find x as a function of t using this result. Using the equation v equals dx over dt, we multiply both sides by dt and obtain dx equals v dt. Integrating both sides with appropriate endpoints, That is, here the initial time is 0 and the corresponding position is x0, and the final time t corresponding to the final position x of t. The left-hand side is nothing but x between the endpoints. This integrand contains t explicitly. This integral can also be written as the sum of these integrals. Now, here a is constant and it can be taken outside the integral. Remember that integral of powered parameters is the inverse operation of derivative of parameters with power n. Since the first derivative of t to the power n is n times t to the power n minus 1, then integral of t to the power n should be t to the power n plus 1 divided by n plus 1. Anyway, the integral of t is then t squared over 2, with corresponding integral limits 0 and t. So the result is t squared over 2 minus 0 squared over 2, that is t squared over 2. Finally, combining these results, we get an expression for x as a function of t as x equals x0 plus v0 t plus 1 over 2 times at squared. If an object is thrown up or down along a vertical axis near the surface of the Earth, we see that it gravitates always towards the Earth because of the downward gravitational force. Neglecting the effects of the air, the object is seen to accelerate downward at a constant rate, which is called the free fall acceleration, or equivalently, gravitational acceleration. We will use the letter G for the magnitude of this acceleration. It is an empirical fact that the free fall acceleration g of an object does not depend on its specific characteristics. That is to say, all objects undergo the very same downward acceleration. Although the value of g changes a little with altitude and latitude, its value near the surface of the Earth is almost constant and given as 9.80 meters per second square. Since the free fall acceleration is constant, all of the formula for constant acceleration that we derived earlier apply also to free fall near the surface of the Earth. For this, we shall label the vertical axis, the y-axis, with its upward positive direction. With this choice, we shall take the downward acceleration to be a as minus g in our formula. As a result, we obtain the following formula for free fall. A is minus g, v is v0 minus gt, y is y0 plus v0 t minus 1 over 2 gt squared, and v squared is v0 squared minus 2g times y minus y0. following consideration might be useful. If an object, initially at rest, is dropped off an elevation of h, and hits the ground in time t, it is easy to show that h is 1/2 gt squared. Finally, in all the problems and examples that will be presented in the video sections and that will be studied in the class, we shall always neglect the effects of air. Okay then, this is the end of the second chapter.